mathematicians who came after Euclid simply tried to prove the postulate. If you prove the postulate, it's no longer an axiom, okay? Because you're proving it from something else. And the most fundamental is that you're proving it from the first four. Okay? There are many such attempts, but that's the way it is. Nobody has ever been able to do so. And then there's also this idea in mathematics, which I'm sure everybody in this room knows, is that the idea is proof by contradiction. That was attempted by many people, like the gentleman whose names are written up there, including the famous Omar Khayyam, who's like a Iranian poet. The idea of proof by contradiction is you assume the postulate to be untrue. In other words, you assume that there's a counterexample to two parallel lines never meet. Develop all possible theorems out of it and hope that you're going to reach a logical contradiction at some point. Once you reach the logical contradiction, that you have proven that theorem by contradiction. Okay? So you have to, in order to go down this road, you have to assume that two parallel lines will meet, or will get further and further away from each other. These are the only two possibilities. And you don't do that by just drawing diagrams. No, you actually start from here. You say, okay, I'm going to assume my first four postulates, and then I will take the fifth as two parallel lines will eventually meet, or two parallel lines will eventually, well, move away from each other, and build a new geometry based on this, and see where it takes me, on the hope that you end up getting a contradiction, in which case you can throw out the fifth postulate and no longer needs to be true. It is such a long story here. I read a whole book once about the story of trying to derive Euclid's fifth postulate over the centuries. It's a fascinating story, and it tells the story of all of these gentlemen who tried to do so, all the way up to the guy who will be interested in today, Riemann. Okay. Well, certain kinds of different types of geometries were discovered in the meantime. For example, if you assume that two parallel lines will get further and further away from each other, then you get a new kind of geometry. You and I can visualize this kind of geometry as being a geometry not on a flat piece of paper. Okay? If it happens to have certain properties, we call it hyperbolic geometry. Okay? Well, hyperbolic geometry, where two parallel lines initially straight, quote unquote, because they're no longer on a flat plane, they can move further and further away from each other. And you can picture this kind of geometry on a surface, or you can picture it in the plane where these arches are in fact what considered to be parallel straight lines in this kind of geometry. Another type of geometry that does not satisfy the fifth postulate is so-called elliptic geometry, where you postulate the other possibility by saying they start out parallel, those straight lines, but then as you get further and further away, they get closer to each other and meet. And once again, you can imagine this as happening on, say, the surface of a sphere. Mathematicians would call it the surface with positive curvature, where every straight line is a great circle on that sphere, and they all meet at the North Pole, for example. Okay, this is kind of a visual to it. And once again, you don't really need to draw diagrams to do this kind of geometry. You can draw it on paper. You just work with the the four postulates, in addition to this modification, and see what happens. See where it ends up being. Well, those so-called non-Euclidean geometries were developed over time by the gentlemen whose names I previously mentioned, and they had always assumed that this kind of geometry must be like a special case or something that can be eventually contain a contradiction, until this gentleman, mathematician Beltrami, proved that they are in fact consistent. In other words, there are no contradictions, it's just geometries. And that's how what we call today non-Euclidean geometry was born. And you have to think in terms of much more than just surfaces with curves on them. We're talking about relationships between curves in any number of dimensions, any number of spaces, and write equations for that without having to draw a single diagram. So people started to be convinced by that time, the 19th century, that, okay, we cannot disprove Euclid's fifth postulate, but we have to say that this is the only one that works in his kind of geometry, which we today call flat Euclidean geometry. In other words, the kind of geometry you and I do on a piece of paper, flat sheet. Okay? But then there are the other kinds of geometries that geometries use, and of course there are many applications to them nowadays. For example, you can do geometry on the surface of planet Earth, for example, kind of non-Euclidean geometry, if you will. But there was an interest in making it as general as possible. We don't just want to talk about curved surfaces like a sphere or like a hyperplane, like the one that I showed you before. We want to write down a relationship or relationships of geometry that would work in any number of dimensions. 2, 3, 4, you know, that's how mathematics works. They don't want to constrain themselves to any number of dimensions. They want a general idea of how to define these non-Euclidean geometries. And this is the gentleman who laid down the foundations of this kind of geometry. Bernard Riemann, and he died around the time our Maxwell was writing down his own equations, and Riemann did not imagine that his work would have any application in physics, I suspect. He is the one who defined the idea of non-Euclidean geometry in a more rigorous way, and introduced a concept that I'm going to show you in the next slide, that today we talk about Riemannian geometry as a special case. What Riemann did was that he was preoccupied with the idea of how to define geometry of a certain surface without reference to higher dimensions. Meaning, here we are living on planet Earth. How do we really know that we're living on a curved surface? Without leaving that surface. I mean, one idea is to just hop into an airplane or a rocket spaceship and go out into the moon and just look at Earth and we'll see that it's a sphere, right? But without leaving planet Earth, how can you define the curvature of planet Earth? Everybody knows about the concepts of seeing boats as they vanish, as they travel over the ocean, and all kinds of things that the Greeks came up with. These are called intrinsic properties of planet Earth surface. Meaning that I don't need to leave the surface to define the curvature. Okay? I can define it with certain quantities that I measure on the surface itself. That's what Riemann was preoccupied with. He wanted to define curvature, he wanted to find the idea of living in a curved space or not by intrinsic properties and intrinsic properties only. And he came up with the following thing. Remember from the very first slide that one of the equivalent statements of Euclid's fifth postulate is in fact the Pythagorean theorem, the very familiar Pythagorean theorem. The square of the hypotenuse is the sum of the square of the sides. Okay? So this is equivalent to the fifth postulate of Euclid in Euclidean space. If you want to go to non-Euclidean space, then this is not going to work, not at least without some modification. Since this is a physics math talk, I'm going to work with differential elements instead. So we look at things in terms of little distances. Instead of delta x's, we replace that with dx's. And of course, you can make it into three-dimensional by adding an extra term. That still works, right? If you want to go to higher spaces, you can. Keep on adding terms, and you still call it Euclidean equivalent to the fifth postulate. In physics, following Riemann, we call this equation the metric, from metrikos in Greek, which means to make a measurement. Because if you review your calculus, this equation is the fundamental equation that you use to measure distances on a surface. That's why it's called the metric. And Riemann was convinced that he can define such a metric for any kind of non-Euclidean spaces. For example, again, to set a visual, consider a sphere. Okay? What do you want to do with the sphere? You want to measure distances on that sphere. But distances on a sphere are no longer flat. As a matter of fact, the shortest distance between 2 points on a sphere is an arc of a great circle. So you need a metric for that. And you need that metric to define the distance without quite making a reference to the outside of the sphere. Everybody knows that this is, in fact, the distance on the surface of a sphere. And we use this kind of thing in integrals and that kind of thing. You need two numbers because it's still a two-dimensional surface. You need the angle of, I call it the angle of latitude, and you need the angle of of longitude, all right? If you think of it in terms of globes. Yes, the radius of the sphere is sitting there, but, and you might argue that this is outside the sphere, but as far as the math is concerned, it's just a constant. Okay, that tells me how curved this thing is. So you can modify the Pythagorean theorem to work on any non-Euclidean surface, any way you want. And that's the basics of defining the geometry of space, any space. Flat, three-dimensional, four-dimensional, I don't care, okay? Here's the summary. The point of Riemannian geometry is that he claimed that all you need to do to define anything about the geometry, be it geometry, sphere, or hyperplane, or anything else more complicated, you just need this metric, and everything else can follow from it. The dimensions of space that you're talking about can follow from it. Your choice of coordinates that you're working with can follow from it. Even the degree of that curvature, which could change from point to point, doesn't have to be constant, right? Also follows from the metric. And all of this intrinsically, that was crucial to him, and it's going to be crucial to us too, without reference to higher dimensions. Higher in what sense? Well, surface of planet Earth going out is higher dimension. It's the third dimension. But if you stick yourself to the surface, you can start figuring out things without leaving that surface, using this metric. So the question now becomes, what geometry do we live in? Okay. And for a long time, everybody had just assumed that the geometry we live in is Euclidean. So if you extend a long rope between stars, for example, you assume that that rope would act as a hypotenuse to a triangle and would work nicely with the metric of Pythagorean theorem. Okay? Parallel lines will stay parallel forever. It's an assumption. Sum of angles of triangle is 180 degrees, an assumption. And the metric is just the Pythagorean theorem in three-dimensional space. That was the assumption. And that was what people were working with. The question is, what if we're not living in a Euclidean space? Well, how would we know? Remember, I'm talking about the universe. I'm talking about three-dimensional space. You cannot leave that and take a picture from the outside. You are in it. Okay? You are, excuse me for the reference, you're an ant living on the surface of a globe. Ant can't fly. Okay? How would the ant know that it's living on the surface of a globe? Okay? So how would we know that we're living in a non-Euclidean space? Well, one thing we can do is to measure the angles of a triangle. Just extend a big triangle and try to measure the angles. If they are 180, then it's Euclidean. If they're more or less, then it's non-Euclidean. Gauss tried this. Tried it with, like, I think, light beams off the tops of mountains and stuff. And he failed. He just found Euclidean. We now know that that's because the measurement was not precise enough. You know, the departure from Euclidean spaces close to our planet is very small. We can notice how objects travel. So on a flat Euclidean surface, an object would travel in a straight line as the shortest distance between 2 points. But on a curved surface, an object is not going to travel on a straight line because there are no straight lines. It's going to travel on a curve. And that curve describes the shortest distance between 2 points on that surface. This is called a geodesic. Okay? Again, from Latin, geo means earth. But you know, it started out as measuring distances on Earth, but now we use that term to describe any curve that describes the shortest distance between 2 points in any kind of geometry, Euclidean or non-Euclidean. So, all of this is nice and fine, hopefully, but perhaps too much math. I need to switch back to physics. This is the physics department, isn't it? I thought so. Okay. What does that have to do with general relativity? Well, it goes all the way back to Newton, who was the first person to realize that the planets orbit the sun because of what he assumed an invisible force that is holding them and just swinging them around the sun like this. And I'm hoping that everybody is familiar with Newton's law of universal gravitation. It's an inverse square law, like you expect the formula to be. All right, sure. Anybody who's taken our classical mechanics class knows that this is the basics of the motion of the planets, and you can calculate. The calculations are long and terrible, but they're all based on one basic principle, that there is this invisible force, quote unquote, that attracts any two objects with mass. Period. That's as far as Newton knew. Okay? Well, the question is, what exactly is happening here? I mean, how does the sun know that the Earth exists so that it reaches out invisibly and grabs hold of it? That is the famous problem of action at a distance. And Newton famously wrote down in his Principia, I frame no hypothesis about the answer to that question. Hypothesis is non-frameable, which means that he was aware of the problem. He was aware that there is action at a distance, and he had no idea what it was. He just said, here's the formula, that's how it works. I don't know what's going on here. He was totally clueless about this. Yeah, there it is. Totally clueless. But he, great scientist he was, he recognized that there was a problem. Now we know there were several, there's a lot of history in between Newton and Einstein. For example, Faraday asked the same question about electric fields and magnetic fields, and came up with the idea of field lines and so on, but still they did not quite explain what's really going on until our hero comes along. I don't mean to hero worship, but this is the central character of this talk. And Einstein, via a series of thought experiments, if you will, which deserve a talk of their own, figured out that maybe there is really no invisible force. Maybe something else that Newton not misunderstood, but mistook for an invisible force because it did not look deeply enough, that is truly responsible for the motions of the planets. The planets are moving on curves, aren't they? Okay? What if they are moving on curves, not because an invisible force is grabbing them, but because they're simply following the shortest distance between 2 points, which would be non-straight if our space is non-Euclidean. In other words, something like a famous picture, I'm sure everybody has seen, of a flat trampoline, and you put some object in the middle, and instead you get a non-Euclidean surface. Okay? I actually have a trampoline, and I did this experiment with my daughter when she was in 5th grade. I wanted to explain to her what general relativity says. So I said, here is a heavy object, we put it in the middle of the trampoline, and we see the trampoline is curved. Now, if the trampoline represents space, and that object represents a heavy mass of the sun, for example, then we can start throwing things towards the sun, and we realize that these things are no longer going to be moving on a straight line. And you can do this experiment. So, have you ever seen this? There's this thing in malls where they're trying to collect your pennies, and you throw it and it goes around and around and it falls into the hole. That's motion in a curved space. You didn't make it travel on a curve. There's no visible force that made it travel on a curve. It's simply following geodesics, the shortest distance between 2 points, but the space itself is not Euclidean. Okay? How can I imagine such a thing? I mean, I can imagine it with a surface like that, with a trampoline, but I can't really imagine it three-dimensionally. What does it mean? I need to see it curving into something else. But that's the beauty of Riemann's idea of intrinsic understanding of curvature. He doesn't need to make a reference to anything outside of the space that he's studying. It's all within that space, and it's all based on this concept of metric. Okay? Now the metric needs to be updated. It no longer looks like the Pythagorean theorem. Look, it's the same idea. The dl squared, but then instead of ones here, there are functions, for example. So you've got here three-dimensional space with coordinates u, v, and w, for example. And then there are functions in here that there are functions in the coordinates. These functions tell me exactly how it is curved. depending on these functions. If the functions happen to be equal to constants or equal to 1, then that's just ordinary flat space, because what you get back is the Pythagorean theorem, as it used to be. No problem at all. So this is, again, a representation of that trampoline, or if you wish, this one. And the dl is, once again, considered to be a distance between 2 points, and in a given set of coordinates can be written down as a modified Pythagorean theorem. That's the idea. So when you spend this kind of mathematics, you study this kind of mathematics, you spend quite some time understanding non-Euclidean geometries. Why? Because that's what Einstein came up with. Our universe is our space, the space that we live in, does not necessarily follow Euclidean geometry. Straight lines are not straight, not really straight. They're geodesic. There's still the shortest distance between points. The planets travel around the sun the way they do because they're trying to follow the shortest distance. And that's it. They were really. Here's the thing: the planets are not under a force. They are free particles. The particles traveling freely in space. They're not under the influence of a force, according to this picture. They're simply following the shortest distance between 2 points because that's what free objects do. If it's Euclidean, the shortest distance between 2 points happens to be straight, yes. That's why Newton's first law, etc. But if it's non-Euclidean, that shortest distance not necessarily straight. There's a redefinition of everything here. So how does one figure out this metric, since everything seems to be hinged on it? Well, it depends on the matter content. So it depends on what is making the space curve. Is it just the sun, or is the sun orbital spinning, for example? Is it something heavier than that? Is it some much more complex collection of matter and energy, by the way? All of these have different metrics, depending on what you want. Do we have a metric for the curvature of space around Earth? Yes, we do. But it's a very, very weak curvature. Earth is not massive enough to bend space in any appreciable way unless you have very precise measurements, which, by the way, has been done. Okay, but it has to be really precise, because the curvature of Earth. That's why Gauss failed by doing triangles that are with angles larger than 180 degrees, because he did not have equipment that was accurate enough for this kind of thing. So after Einstein came up with this idea, in 1915, I think the paper was published early 1916, and there was the big question of how does one calculate the metric for a given situation? Give me a star, or a heavy object, or some configuration of matter and energy, and I should be able to calculate the metric. So there was a big race, I remember reading about it, between him and the famous David Hilbert, about who's going to answer that question. They both knew about the curvature of space, and that was done. So, okay, now we know what's happening. But now I need a mathematical way of calculating this curvature, or calculating this metric. And that's what Einstein came up with. Okay, he beat Hilbert by a few months. He published a paper which had this equation. Now, I can't really explain that equation for you because it takes a while just to develop the stuff that we need to understand this equation. But all you need to know about it is that the left-hand side is a quantity with a lot of stuff in there, and a lot of second derivatives in there, and it represents how space is curved. While the right-hand side, this T object, contains, again, information inside, encoded in there, that represents the matter and energy content. So essentially what you have is a second order differential equation in the matter content. Something like, in classical mechanics, something like Poisson equation. Second derivative of something is equal to matter content. This is pretty much the same thing, although this actually represents 10 differential equations, not just one. They're all written just concisely like this. They are highly nonlinear, which makes them even more difficult to solve, and they're all partial differential equations, and the solution is the metric, depending on what the matter and energy content is. Okay? A lot of fun hours can be spent solving these differential equations. Okay? Does it fit with the previous picture of Newtonian gravity? Yes, it does. As a matter of fact, you can extract Newtonian gravity, all of it, from this equation. F equal to GMM over R squared is in here, but only comes out if the curvature of space is very low. And that was all that Newton was aware of. Low curvature. He recognized it as such, even though it was hidden in his equations. Okay. So the consequence of all of this is that this is a summary of what I've just described to you. And one of the major consequences that perhaps I haven't mentioned is that not only objects with mass can travel on these geodesics, like the planets, but it turns out that also non-massive objects, like light. Light doesn't have a mass, doesn't have a rest mass. So even light can curve in space because it's still following not a straight line, but the curvature, the shortest distance between 2 points. And all of these were verified experimentally. I will tell you a little bit about observations that prove that all this is true. There are some classic ones, like explaining the orbit of Mercury, like explaining the bending of light during the 1919 eclipse, but these are so common, I'm going to skip them and show you some modern ones. For example, this. The most exotic of all possible predictions of the general theory of relativity, the black hole. How many movies were made about black holes? The idea of a black hole is that it is an object that has curved space so much that there is a point of no return, a certain sphere or a surface around it where if you enter, you can no longer escape. Traditionally, this is explained by saying that the escape velocity from a black hole is larger than the speed of light. But that's not very accurate. There are better ways to explain this. It requires a little bit more time. The point is, a black hole is not an object. It is a quantum, it's an object made of space-time itself, space itself. Space with really high degree of curvature. You can imagine it like this. Here is our old model, the trampoline. You have a star, it bends space in a certain way. And don't ask me where does it bend into. This is just a schematic. Okay, it doesn't bend into anything. Okay, there is no drop here. This is just a schematic to tell you how extreme the curvatures are. So this is a usual star. The more massive an object and dense an object, it has to be massive in a very small volume, then the more extreme the bending is. Both of these curves are described by this metric. Okay? But then, if you have an object with such a high concentration, then it bends it so much that you cannot even see the end of this throat anymore. It goes all the way down to infinity. Kind of blows up in our faces. The curvature at the center of this object is, in fact, well, infinite as far as we know. Okay? Still described by the same object, by the way, but now the curvature of space is so extreme, this one is described as a black hole. Okay. Black holes are such exotic objects and very interesting that, you know, I have talks, just several talks dedicated just to black holes because there's so many fascinating properties here. For example, what do you see if you're falling in a black hole? What does somebody see happening to you as you're falling in a black hole? Not the same thing, by the way. Right? What happens if you shine a beam of light towards a black hole? Hint, it slows down and stops at some point. Stops. Etc. There's so many fascinating things, but we have to move on. The black hole schematic I showed you in the previous slide was for a static black hole. It's not doing anything. But this would be representative of a black hole that is spinning. Not just a black hole. Any spinning star would have a metric or a space-time around it that is kind of swirling like this. This is called the dragging of frame dragging of space itself. And again, that has been experimentally verified for Earth. For Earth's dragging of space around it is very small. It requires very precision measurements, but it has been measured. But this is what a schematic of a spinning black hole would look like. Now, you might be wondering, if it's a black hole, what is this light? Well, usually these lights are drawn to represent matter that's in orbit around the black hole, like a lot of dust. And they are all spinning around it and eventually spiraling down into the black hole. But because they're spinning around with such high speeds, they rub against each other and they generate all kinds of
electromagnetic radiation, mostly X-rays that reaches the Earth. So we usually draw these kinds of, they call them accretion disks around the black hole, even though the black hole itself cannot be seen. But something like this is, they call it an active black hole. It's a black hole in the process of eating, quote unquote, something. Do we know that these things exist? Yes, we do. Actually, as a matter of fact, not only do, we have pictures of them, real pictures, not taken with a cell phone, and definitely not visible light. Okay, they've been translated into visible light for your viewing pleasure, but they're not real light that comes out of the black hole. These are actually radio waves that come from very distant black holes. The black holes were observed before pictures were taken. And two groups of scientists who won the Nobel Prize in 2020 had proven that at the center of every galaxy there is a supermassive black hole. And we really need supermassive. We're talking billions of times the mass of the sun, of our sun, at the center of every galaxy. And the reason they observed them is that they didn't see them directly. They saw the effect they had on the spinning of stars around them. Stars are in orbit of black holes, just like the moon is around the orbit of the Earth. But that's boring. This is more exciting, because it's actually taking photographs of it, and it was done a few years ago. We have now two pictures of two different black holes. This one from a distant galaxy called Messier 87. It's the M Messier is a wave cataloging stars. And that was the first picture of a black hole taken a few years ago. I think it was 2018. And then recently, 2 years ago, this is the black hole that is at the center of our galaxy, the Milky Way. Sagittarius A star, it's called, because it lies in the constellation Sagittarius. Again, I have another talk about how to take pictures like this, but the point is, this one is another galaxy, while this one is our black hole, our resident black hole, the center of the galaxy. People always wonder, why take a picture of a distant one first, and then take a picture of a closer one? Wouldn't this be easier? Why not?
Because all the stuff that's in our galaxy.
Bingo! Yes! All the stuff between us and our central black hole is in the way. It's much harder to take a picture of that. But if you look perpendicular to the galaxy, there's empty space all the way to M87. All right? That's why it was actually easier to take this picture than it is to take that one. And once again, the light is this accretion disk, this rubbing matter that is falling down and generating like high energy electromagnetic radiation. So that is one incredible verification of this idea of the bending of space. The second one I've chosen to tell you about, and I hope I'm not running out of time, is the discovery of so-called gravitational waves. Another thing that was predicted by Einstein himself. Einstein thought that if space that we live in can bend and curve, what happens if you knock on it on one side, right? If it's elastic, then you expect ripples. Ripples in space itself. Space itself is rippling. Can you imagine this? Right? I mean, mind-blowing. He predicted that these gravitational waves must exist, but he also predicted that they are extremely weak. They needed to be detectable, two things: very accurate measurements and a catastrophic event. That happened in 2016 when the so-called LIGO, the Laser Interferometer Gravitational Wave Observatory, said that all at once without stumbling, started working, and it's essentially a Michelson-Morley experiment for gravitational waves. It's essentially what it is. You see two arms like this, and they interfere the waves. It's such a precise instrument that a car 500 miles away can cause vibrations that will affect the results of this light. The work that was done is incredible. These three gentlemen took the Nobel Prize the next year right away once they detected. This is the first time, I think, in history where the Nobel Prize was given the following year to a discovery. Usually they wait decades before deciding. But everybody was so excited because that was the one final unverified prediction by Einstein's idea of curvature space that was not done. You may know that this guy, Kip Thorne, who was the scientific advisor for the movie Interstellar, right? And he's the one who designed the way the black hole looks like and so on, and that happened. He wrote a book about it and published papers about how to present black holes in movies. That's why I always say it's one of the most accurate movies that I've ever seen in terms of space-time physics. The event that they detected was of catastrophic size, magnitude. It is the collision of two black holes that happened millions of, I think 2 billion years ago. It's spinning around each other, high speeds, incredible speeds, approaching the speed of light, and then they bump into each other, they generate ripples of gravitational waves that they reach us. This is a screenshot from the actual paper, which doesn't look as interesting as this, which is just a schematic to tell you what these starting points. I think, and a lot of people think, I believe, is that we have now in our hands a new kind of astronomy. Think about it. All astronomy to date is based on electromagnetic waves, right? And now we've discovered another way of detecting astronomical and cosmic events that does not depend on electromagnetic waves, doesn't depend on visible light, doesn't depend on radio, X-rays, none of these. Pure gravitational waves. This thing is the telescope of gravitational waves. And we are right now in the few years after the invention of the telescope. And everybody knows what happened after the invention of the telescope. Galileo, all that stories of that. Discoveries just exploded. This is where we are right now. So we're looking into a really good, I think, future in terms of these things. There are other solutions of general relativity. Let me skip that one because it's not been verified. And just go straight into one last thing before we conclude. I haven't mentioned time at all in this talk. I was focusing on just space. But I have to tell you that the effect of the curvature doesn't just affect space, it affects time. The metric that we spoke of a few minutes ago has an extra piece. And that extra piece depends on the measurement of time, dt, right? There's the speed of light c here, just put in to make the units correct. But this is the fourth dimension, if you will. The Pythagorean theorem, which is everything minus this, becomes that if you include the effect of time, okay? Which means that every metric, even the ones that I showed you before, there has to be an extra piece with the effect of time in it. So this is the black hole metric that I showed you before. It's got a lot of stuff in it, and there is an extra piece with time as well. But that means that time is also affected by the curvature of space, because now we're not just talking about curvature of space alone, it's curvature of space-time, just one word. And yes, it is affected. Measurements of time could be slower or longer depending on how strong the curvature of space-time is. And again, that has been measured and verified. So that was the only missing piece. Here is an example of how time is affected. How time is stretched by the presence of massive objects, is that if you're closer to the center of a massive object, like say the ground floor of a building, and somebody else lives on the top floor of the building, time passes differently. Sure, on Earth you don't really observe this, but technically if you live closer to the ground, you live a little longer by a few picoseconds for a lifetime, something like this. But if you're talking about a black hole, that's a significant difference. Remember Interstellar? Huh? One day on that movie, on that planet was what, like 10, 15 years on Earth or something like this? This is a real thing. This is counted. And so this effect of bending time happens and can be measured. Yeah, so that's pretty much it. And now we are at a point where we have this tool which describes the curvature of space-time. And a lot of things can come out of it. For example, there are possible ways, kind of unlikely, but possible ways to find time travel in Einstein's theory of relativity. There are possible ways to imagine even higher dimensions and parallel universes. We step into what I call Star Trek universe, Star Trek physics, essentially. Why is it, open questions, why is it that the geometry of space-time behaves like this? Why is it that massive objects bend space? Nobody knows. There are questions of topology of space-time. It's a whole branch of mathematics by itself. Is it closed? Does it have holes in it? Does it have things like that? And all kinds of other theories came out of this concept, like search for how to reconcile quantum gravity and string theory and other things that I may have time to talk about in the next talks if people are interested. So yeah, that's the tip of the iceberg, as I So hopefully, thank you so much. And I wonder if there are any questions. Any questions, or are we all went to guys' question? Yeah.
So I really like your analogy of the ant moving around on the surface of the earth and kind of asking, how do I know I'm on a
Yeah.
spherical object, right? And you can imagine, the ant walks in a straight line and eventually comes back to where it starts and it figures
That's one way. Yeah.
curvature.
But that's a curve, the global way of figuring things out.
Exactly. So another question would be, how does the ant know that it's walking on a curved surface that is also rotating? And it could do little physics experiments and look at things like Coriolis force and notice if there's an asymmetry depending on whether I move east or west or
Yes.
something like that. And so expanding that analogy out to the entire universe, my question is there any experiment we can do to understand whether the entire universe itself is rotating?
I suspect that there must be, but unless it's rotating really, really fast, I think we're going to need some very, very accurate experiments there. And I suspect it's going to be something along the lines of Coriolis, because there would be frame dragging effects, just like the spinning black hole or the spinning object. It drags space-time around it. So the universe is spinning. That spinning cannot happen everywhere at the same time. It's got to propagate. You know what I mean? It also will pick a preferred direction, which means that the universe fails to satisfy isotropy, not isotropically, which would have dire consequences in cosmology.
Yeah. Is there any, do you know if there's any sign of
Now,
asymmetry?
there is large-scale asymmetry in the form of galaxies that how galaxies structure themselves on a very large scale. There are voids and there are filaments of galaxies on
Yes.
extremely large scale,
Yes.
full velocity structure. And that's thought to be, and that's another talk we can do, thought to be the reason it happened very early in the universe because of small quantum fluctuations that kind of redistributed things and broke the symmetry on a very large scale. On a medium scale, somewhere between 100 megaparsec and 300,000 megaparsecs, the universe is completely uniform and homogeneous. But if you look much further than this, you start seeing those big voids and big filaments, which breaks the symmetry in a sense.
Yeah.
There's also something called the axis of evil. Not that kind of axis of evil, but it's called axis of evil because it's really crazy. It is the idea that the CMB, the cosmic microwave background, may have a preferred direction in one of its multiple expansions that aligns itself with the ecliptic plane. That's what's called the axis of evil,
We're not
because
sure
it
if
seems
it's
to
an
indicate that
observational-
makes us special in a way.
Yeah.
And it's still a big question mark. People think maybe there's a mistake in the measurements and one of those mysteries. So choosing a preferred direction in space is problematic in many ways. But if it is, then it is.
I have, you were talking about the experiments on the Earth to find out if it's curved, and you're talking about taking measurements across an ocean or something like that. But those involve elevation, those would be extrinsic.
Yes.
Not
Yeah, I'm talking
intrinsic.
about like drawing triangles, spherical triangles, and measuring the angles. So these are intrinsic because you're connecting geodesic lines,
Okay.
and that would give you a triangle with larger than 180 degrees.
My other question is probably
Without
something
being-
everybody else here knows, but, I hear about that static and rotating black holes.
Right.
Are we talking, is the singularity rotating? Is the event horizon
Space-time,
rotating?
yes.
Or is it just lumpy on the inside? It seems like if it was lumpy on the inside, the event horizon would just be spherical over here instead of over here.
Would be like this.
Okay,
Oblated forward, just like Earth.
okay.
That would be the event horizon of a spinning black hole.
Okay, so we would know that it was spinning by its oblateness.
We would know it was spinning because there are two reasons for this. For example, everybody assumes in astronomy that everything in space has got some kind of angular momentum. Slow or fast. It's an assumption because it's such a random thing. So that's one thing. The other thing is, if something is falling into it, and you can observe the trajectories of these things, they would be slightly different from a static black hole than they would be for a spinning black hole, because they're being dragged around in space.
Okay.
But my understanding is that the measurement is so the difference is so small that it's kind of hard to see it from the pictures that we have. We're gonna have to get up close and personal, which is not always a good idea.
Send me in.
Send you in. I don't think you would want to go in. All right.
I've got a couple of questions that I want to hold out there. The first one of those is rather pedestrian questions, so you said